My name is Jeshwar. I am from CSC Department B section. Today our topic is two-dimensional photonic crystal lasers with center rectangular lattice structure. Introduction to photonic crystal lasers. Photonic crystal lasers utilize periodic dielectric structures to control light propagation. They offer high efficiency, low threshold, and tunable lasing characteristics. Two-dimensional photonic crystal lasers are particularly promising for integrated photonic applications. Basics of photonic crystals. Photonic crystals are materials with periodic variations in refractive index. They create photonic band gaps that prohibit light propagation at certain frequencies. These properties enable precise control over light within optical devices. Two-dimensional photonic crystals. 2D photonic crystals have periodicity in two dimensions with finite thickness in the third. They are fabricated using techniques like lithography and etching on thin films. They are ideal for surface emitting lasers and integrated photonic circuits. Center rectangular lattice structure. The center rectangular lattice features a rectangular array with additional points at the center of each cell. This structure provides unique symmetry properties compared to simple rectangular lattice. It allows for more versatile bandgap engineering and mode confinement. Lattice geometry and parameters. The center rectangular lattice is characterized by two lattice constants are A and B and a centered point within each cell. The lattice symmetry belongs to the C-2V point group. Adjusting A and B allows tolerating of photonic band gaps and mode localization. Photonic band structure in center rectangular lattices. Band structure are calculated using methods like plane wave expansion or finite differential time domain FDTD. The centered rectangular lattice exhibits multiple band gaps suitable for lasing. Band gap width and position depend on the lattice parameters and dielectric constraint. Mode localization and confinement. Defects introduced into the lattice can localize photonic modes within the bandgap. These localized modes serve as optical cavities for lasing. The center lattice geometry enhances mode confinement and quality factors. Fabrication techniques. Common fabrication methods include electron beam lithography, reactive ion etching, and thin film deposition. Precise control over lattice parameter is essential for desired optical properties. Challenges include maintain high structural fidelity and minimizing defects. Advantages of centered rectangular lattice lasers. They offer flexible control over bandgap properties and mode profiles. The lattice symmetry allows for polarizing or polarization control and multiple mode operation. Enhanced mode confinement can lead to lower lasing thresholds. Lasing mechanism. Lasing occurs when optical gain exceeds losses within the defects modes. The photonic band gap suppresses unwanted modes, enhancing laser coherence. The centered rectangular lattice facilitates efficient feedback and mode selection. Design considerations. Optimizing lattice parameters for targeted emission wavelength is critical. Material choice impacts the refractive index, contact, and lasing efficiency. Incorporating active gain media such as quantum dots or dyes is essential for lasing. Simulation and modeling. Computation look tools like FDTT simulate electromagnetic behavior in the lattice. Band structure calculations help identify suitable defect modes for lasing. Simulations guide for the optimizing of cavity design and lattice parameters. Experimental demonstrations. Several studies have demonstrated lasing in centered rectangular photonic crystal structures. Achieved lasing wavelengths typically range from visible to near infrared. Experimental results show low thresholds and high coherence in these structures. Applications of 2D photonic crystal lasers used in on-chip optical communication system for integrated light sources. Applied in sensing due to their high sensitivity to environmental changes. Utilized in quantum information processing and optical computing. Challenges and limitations. Fabrication imperfections can reduce quality factors and lasing efficiency. Achieving uniform defect modes across large areas remains challenging. Thermal management is necessary to prevent performance degradation. Future direction in research. Developing novel material with higher refractive index constraint. Exploring three-dimensional lattice configurations for enhanced control. Integrating active turning elements for dynamic control of lasing properties. Comparison with other photonic lattice structures. Centered rectangular lattices offer more design flexibility than simple square lattices. They outperform hexagonal lattices in certain mode confinement scenarios. Each lattice type presents unique advantages depending on application requirements. Summary of key benefits. Centered rectangular lattice structure facilitate versatile and efficient photonic crystal lasers. They enable tolerated photonic bandgaps and high quality mode confinement. Ongoing research continues to improve fabrication, performance, and integration. Conclusion. Two-dimensional photonic crystal lasers with centered rectangular lattices represent a promising technology. Their unique symmetry and adjustable parameters open new avenues for photonic device engineering. Continued advancements will lead to broader practical application in photonomics and optoelectronics. Reference and acknowledgements. Key lecturers include recent, recent journals, articles, and reviews on photonic crystal laser design. Acknowledgement to research groups and institutions contributing to this field. For further information, consult specialized texts and recent performance proceedings. I hope you understand this topic.